Welcome! First video, first topic, we're going to talk about matrices. What are matrices? Well, on a very formal level, a matrix has this shape. It's usually defined by a capital letter, and it's a box of values. We write it like this: it belongs to R at the power n times m. When n in the number is the number of rows you have, m is the number of columns. Each combination of row and column is a value. In this case, I wrote R, so we say that each element is a real number, but it can also be complex. For most of the applications, we'll go only looking at real values. So a matrix is a box of which we know the rows and the columns, and each row and column is filled up with a real number or a complex one. We have a bunch of different notations to compact this thing because writing the full matrix all the time is usually painful. So here at the bottom, you have some notation. The first one is the most general. It tells you that capital A is equal to the values little a with index I and j, with I spanning the columns, so going from 1 to n, and I spanning the rows and j spanning the columns. So I is going up to n and j is going up to m. If we have already defined the size, we can write capital A with parentheses and the indices, or A equals ij with some I and j, if we already know the dimensions. What are properties of matrices? The very basic ones. First, when are two matrices equal? So if A is a real matrix with n rows and m columns, and B is a real matrix with k rows and l columns, first of all, you need the number of rows and the number of columns to be the same. If they don't have the same size, they cannot be equal. And then you need every single element inside the matrix to be matching, one by one. When is a matrix zero? A matrix is zero if all the elements in the matrix are zero. Can we add matrices or subtract matrices? Yes, we need them to be of the same size. So again, the same number of rows and the same number of columns. Then we define a new matrix that has the same number of rows and the same number of columns, in which each element of the new matrix is the sum of the two elements in the same place of the starting matrices. We also define transposes. If A has n rows and m columns, the transpose has m rows and n columns, so we flipped. And we define it as the flipping of indices. So the transpose index ij is the original matrix at position ji. The conjugate is something that we define for complex matrices and therefore for every matrix. And what we're taking is for every element in the matrix, we take the complex conjugate. If we put transpose and conjugate together, we talk about adjoint, is the transpose and conjugate. For matrices, we have scalar multiplication. So if we take a value in R, a real value, and a real matrix, you can multiply this together. And you do that by just multiply every single element in the matrix by the scalar you just indicated. That means that this type of multiplication is distributive with respect to addition. That means that if you have a scalar multiplied by the sum of two matrices, is the same as having the sum of the two matrices multiplied by the scalar. Can we have matrix multiplication? So a matrix multiplied by another matrix. A times B, where A and B are matrices, only work if the number of columns of A is the same as the number of rows of B. So in this case, it's A has n rows and m columns, and B has k rows and l columns. We need m equals to k. If that is the case, then we can define a new matrix that has the number of rows of A and the number of columns of L. And each element of C is defined in this way. So you're fixing the row of A, fixing the column of B, and then you take each element in the specific row that you fixed in the specific column, and you multiply them and you sum them all. In general, A times B is different than B times A. Actually, you can have the situation in which one of the two exists and the other doesn't exist. Let's do an example of multiplication. So we have a matrix 1, 2, 3, 1, 3, 4, and a matrix 1, 2, 1, 4. So A is in the real, it's a real matrix with size 2 times 3, 2 rows and 3 columns, and B is in 2 by 2, 2 rows and 2 columns. Because the size of A and the size of B are not the same, A plus B does not exist. You just cannot define it. A times B does not exist because A has 3 columns and B only has 2 rows. But B times A actually does exist. Let's go and check it out. We're multiplying B times A, so we're multiplying 1, 2, 1, 4 times 1, 2, 3, 1, 3, 4. And the first element is the first row of the first matrix times the first column of the second matrix. So it's 1 times 1 plus 1 times 2. Then the next element is the first row of the first matrix times the second column of the second matrix. So it's 1 times 2 plus 2 times 3. And then we keep going. So the third element in the first row is the first row times the third column. 1 times 3 plus 2 times 4. And now we go to the new row. We are taking the second row of the first column and we're multiplying it with the first column to get the first element, the second column to get the second element, and the third column to get the third element. And this is what comes from it. 1 times 1 plus 4 times 1 for the first element. 1 times 2 plus 4 times 3 for the second element. And 1 times 3 plus 4 times 4 for the last element. Let's go now into vectors. Vectors are, you can think of them as just one column of a matrix, or a matrix with just one column. Most of the things we introduced for matrices hold for vectors in the trivial way. So you can go from matrices to vectors very straightforwardly. Some things don't, and we're going to focus on those ones. So the things that translate directly from matrices to vectors are equality, the zero vector, the addition between two vectors, and the scalar multiplication. So the multiplication by a real value. But we also have the topic of vector multiplications. So we're taking two vectors and we want to multiply them with each other. There are two types of multiplication between vectors. Both types requires the vector to be of the same size, of the same shape. The first is a dot product. We have a vector x and a vector y. And if we say x dot y, then what we do is we take the transpose of x. So we have said that a vector is like a column of a matrix. The transpose of a vector is just a row of a matrix. And then we multiply x and y with the matrix product. They only have one row x transpose and one column y, so we only have one element. With this dot product is commutative. That means that x times y is the same as y times x. And you can notice it by the formula. It's just a sum over all the indices of x and y. So xy times yi, y, and you sum all of that. We have what is called the internal product. It's usually defined for complex vectors. It's similar to the dot product in the sense that x internal product y, it's x transpose times y, but this time we take the complex conjugate of y. Notice how these are the same if you are in the reals. So real vectors have the same approach. It doesn't matter if you're taking the dot product of the internal product. It only matters if you're looking for complex vectors. The norm of a vector, it has a lot of other names to it. The magnitude, the length, is the internal product of the vector times itself at the power 1/2. So it's the square root of x times x. Notice how this comes very naturally if you're thinking of absolute values in the real or the complex value numbers. You take x, you multiply it by itself, and you take a square root. That is the absolute value. And the norm is the extension of absolute values to vectors. If you're taking the dot product, then two vectors can be orthogonal. So you can have vectors that are not zero and which product between them is equal to 0. They're orthogonal because if you're looking at them in the plane, what you're looking at is perpendicular vectors. If you take two perpendicular vectors and you do the dot product between them, then their dot product is equal to 0.